Welcome, everyone. I'm Liz Stewart from Johns Hopkins Bloomberg School of Public Health. I'm one of the Methods Core co-directors of the ALACRITY Center. The ALACRITY Center is funded by a National Institute of Mental Health P50, PI Gail Dommett, who is joining us today as well. And again, this is part of a webinar series that we have on advanced methods, including YouTube video recording. So this session is being recorded, and we will put the main sort of content up on the YouTube page when it's ready. We will also put a link to that YouTube page in the chat so that those of you who aren't familiar with that can see the other sessions in this webinar series and benefit from them. So again, I think I've already said this, but welcome. We're really happy to have you here today, those of you who can join us live, and then also anyone watching the recording later. And again, this is hosted by the Johns Hopkins ALACRITY Center for Health and Longevity in Mental Illness. Just a little bit on the ALACRITY Center itself. Again, this method series is part of the Methods Core. More broadly, the ALACRITY Center is a research practice translation center designed to address this problem, the wicked problem of premature mortality and medical comorbidity among people living with serious mental illness. The aims, overall aims of the center are here. The webinar today is particularly relevant for bullet 4, but more broadly, the center is interested in planning and testing and is doing planning and testing implementation strategies to implement and scale evidence-based interventions into community settings, again, with this focus on longevity for individuals with mental illness. A strong focus on community partnerships for adapting, implementing, and planning for broad dissemination of interventions, building capacity amongst mental health researchers and community partners to advance health for people with serious mental illness, and then advanced methods for implementing and scaling evidence-based interventions. So again, this webinar series really is about the interface of those third and fourth bullets, where we have had a series of webinars on methodological topics that help advance research in these areas. So again, here you can see on the YouTube channel our set of other workshops. They include things like interrupted time series methods, propensity scores, and other things. So we welcome you to check those out. I am going to stop talking. And I'm really happy to be joined here today with our two leads who are going to be talking about today's topic, which is covariate adjustment in randomized trials. And I'm excited about this topic because it's an area of a lot of interest in many fields, especially sort of a more, I would say, medical and sort of FDA focus. There hasn't been much translation of these ideas to a sort of mental health services sort of world. And so I think this webinar is really designed to help start that bridge. So I'm happy to introduce Michael Rosenblum, who's a professor in the Department of Biostatistics at Johns Hopkins, and Josh Betts, who's associate scientist in the Department of Biostatistics. They are really two of the world's experts in this area. And so they're going to be leading. Michael will be primarily leading the presentation, and Josh is here for additional great insights and help. I will turn things over, but one quick organizational piece. If you have questions throughout, we're gonna do the sort of main content, sort of kind of straight through for recording purposes. Josh will be monitoring the Q&A throughout. So if you have questions, feel free to put them in the Q&A. You might get a response quickly and sort of a little typed response. We will then also have some time at the end for more of a sort of open discussion and Q&A, and we'll go back to any of the questions that come in that we hadn't answered already. So please engage, put questions in the Q&A, and I will hand things over to Dr. Rosenblum for today's presentation.
Well, thank you for the kind introduction. And it's an honor to be here, to be presenting. And all this work, I'll share my screen. All the work is with Josh Betts. The work is also with Kelly Van Lanker, and she's in the Department of Mathematics, Computer Science, and Statistics at Ghent University. And I should give the disclaimer before I go on that the opinions in this presentation, they're just ours, myself, Josh Betts, and Kelly Van Lanker. They don't necessarily represent Johns Hopkins University, the FDA, the NIH, HHS, or anyone else. And I mentioned FDA in there because we have collaborations on these kind of topics with the FDA, and I'll talk about some FDA guidance documents. And the bulk of my research, a lot of which I do with Josh Betts, is on trying to find improved methods for designing and analyzing randomized trials. And the context here is choosing an analysis method for a trial that you're designing. So that I've been told that some of you, maybe many of you, design or work on or lead clinical trials, randomized trials. And when you're designing the trial, you need to put in the statistical analysis plan, how will you analyze the data for the primary analysis at the end? And that choice often, it doesn't get enough attention because it can have an enormous impact on the final outcome of the trial, on the conclusions. And so what I'll talk about today is methods to put in your statistical analysis plan that will be used at the end of the study as your primary analysis of the effect or not of the intervention or treatment that you're testing. And some recommendations on some methods that can provide substantial advantages over others, but are highly underutilized. Even though the FDA generally supports using them, and so that's the context. And so this is the simplest example of an analysis method would be, say, take the difference between the mean of the outcome in the intervention arm versus the control arm. But sometimes you can do a lot better than that. So that's the idea. And we also want to essentially make recommendations on how to do the best analysis, so you can get the most information out of your data. And if the intervention really works, then it will help you figure that out. If it really doesn't work, it will help you figure that out as well. And so part of the motivation here is that there's an FDA guidance from 2023, so just a couple of years ago in May, a guidance on adjusting for covariates in randomized clinical trials for drugs and biological products. And a quote with a boldface that I added is, covariate adjustment leads to efficiency gains when the covariates are prognostic for the outcome of interest in the trial. Therefore, FDA recommends that sponsors adjust for covariates that are anticipated to be most strongly associated with the outcome of interest. So this is all I'm going to be talking about is our ways to do this. And actually this recommendation, it dates back to, it's not a new idea. It goes all the way back to recommendations from the FDA in 1998. And so I'll talk about some of the history of it. This is not a new idea. I did not invent this idea. It's been around for a while, but it's the reason I'm passionate about this. And I'd like to, Josh and I, and sometimes Kelly Van Lanker, we give short courses. We're giving one next week for the American Statistical Association Biopharmaceutical Industry Workshop, and try to train statisticians on this and try to help. You don't have to be a statistician to appreciate it. But we try to spread the word on this and develop improved methods for how to do it, the specifics of doing it, because a while back we realized that the improvements you can get, so what you essentially are going to get out of this potentially are improved analyses that give you tighter confidence intervals. So you have a better understanding about what the true treatment effect is. And that potentially you need a smaller sample size to get the same power in your trial as if you compared to if you didn't use the improved method, the covariate adjusted analysis. So and the improvements are not just a 1% improvement, even though it would be worthwhile to do it even for that. But I wouldn't be giving this talk in that case. I wouldn't be as excited. But sometimes the improvements you can get are quite large. So in some, it depends on the disease setting, on the outcome, what the primary outcome is, the population, and if you have good baseline variables that are correlated with the outcome. But in some cases, which I'll talk about, using this improved analysis, it's equivalent to needing 25% less sample size to achieve the same power. And all you're doing is just in your statistical analysis plan saying, I'm going to use this analysis as my primary analysis. And it can get you, if you think about it, it's always very difficult to recruit participants, and trials can last quite a long time. And so something like a 20% reduction in the sample size at no cost can be quite substantial. I'd say so that's why we like to talk about this, because the effect can be big and it's underutilized. And so the overview is that covariate adjustment, that here's what it means, the first bullet point. And the context, again, this is only in randomized trials. And I'm going to talk about individual level randomized trials. Individuals are randomized to, say, a treatment or control, so you can extend it to more than 2 arms. There are applications in cluster randomized trials where centers are randomized to an intervention. But here we'll talk about and that's work in progress through the ALACRITY project center. But I'll focus on individual level randomization because it's simpler. And the goal is to estimate the average treatment effect. What if everyone in your target population had been assigned to a treatment? What would the average outcome be versus had everyone been assigned to control in your target population? And the first bullet point explains what covariate adjustment is. It's pre-planned adjustment for baseline variables when estimating the average treatment effect in the primary efficacy analysis. Efficacy analysis is the analysis of what is the effect of the intervention. Does it improve health or not? That's opposed to a safety analysis, which would be looking at something separate. And what's not something I try to emphasize and is the second bullet point, and this is recommended by someone at the FDA. They told me as a side thing that they wish people would absorb this, and that the interpretation of the estimated treatment effect using covariate adjustment, at least in the context of this talk, it is for average treatment effects, it's the same interpretation as when you use a simple unadjusted estimate. So unadjusted would be, estimator would ignore baseline variables. It would just look at, say, the difference in the sample mean of the primary outcome in the treatment arm versus control arm, and say take the difference between those. So when you do it, you can do another estimator of that going after the average treatment effect with covariate adjustment, which we'll talk about, that the interpretation is the same thing. You're trying to estimate the same thing. You're just doing a potentially better job at it because you're squeezing out some more noise, which helps you see a signal if there is one. And so the third bullet point, you can improve precision and reduce the required sample size to achieve a desired power. And another takeaway is that you can use covariate adjustment for many types of outcomes. So here I'll talk about, because it's the simplest case, a continuous valued outcome. But you can use covariate adjustment for binary outcomes, 0, 1 outcomes, ordinal outcomes, 0, 1, 2, 3, some scale, time to event outcomes, essentially any type of outcome in a randomized trial, you can use covariate adjustment to potentially improve precision. So these 4 points are the ones that are the main points in the talk. And just to give a little more background, and before diving into how do you do covariate adjustment, the use of covariate adjustment in randomized trials, it varies quite a bit. Pocock et al. Back in 2002, they surveyed 50 randomized clinical trial reports. They found that the statistical emphasis, well, this is a quote, the statistical emphasis on covariate adjustment is quite complex and often poorly understood, and there remains confusion as to what is an appropriate statistical strategy. And Austin et al. In 2010, they did something similar, a similar survey, and found a similar results that their paper title describes it pretty well. The title is "A Substantial and Confusing Variation Exists in Handling of Baseline Covariates in Randomized Controlled Trials." It was a review of trials in leading medical journals. And so there's a lot of there are some misunderstandings out there, confusion about when one should use covariate adjustment, how to do it. And so that's part of the talk. And Josh and I are one of our goals is to try to dispel some of the myths, some of the incorrect things people think about covariate adjustment, and to try to get it used more often where it can have an important impact on improving trial, the information that's generated by randomized trials. And it's essentially to everyone's benefit to use this method. FDA appreciates it. I mean, I don't speak for FDA. I said in the disclaimer, but if I were at the FDA, I would want people to use covariate adjustment when you have prognostic baseline variables, because it squeezes out noise and helps them do their job of figuring out does a particular treatment, does it have a benefit, and what is the benefit, if so. And so the targeted inference, this is also an FDA recommended thing before you start talking about estimating how you're going to estimate, what estimator you'll use, talk about the estimand. What is the target? What are you trying to estimate? And so here it's the population average treatment effect. It's a contrast between the average, some summary of the outcome distribution if everyone had been assigned a treatment versus control. It's sometimes called the intention to treat estimand, and so it could be that if you had access to the entire target population, if you could assign all of them to treatment and then measure their outcomes, and then go into time machine, go back, and instead intervene on yourself and have everyone be assigned to control and measure their interventions, you're interested in what the difference would be. But since you can't do any of that, you do a randomized trial to try to estimate, to try to get at that average treatment effect. And the bottom line on covariate adjustment is this third point, that if baseline variables are prognostic for the outcome, that just means correlated with the outcome, unrelated to the treatment. This is just talking about, do you have variables, for example, risk factors measured at baseline that might make someone more likely to have a bad outcome, regardless of what they're assigned to, treatment or control. So if their baseline variables are prognostic for the outcome, then covariate adjustment has potential to substantially improve precision. You get shorter confidence intervals, reduce sample size, and reduce trial duration compared to not adjusting for baseline variables. And the whole idea is that the intuition behind it is that you can gain precision by adjusting. What's happening is you're adjusting for potential chance imbalances between the treatment and control arms in these prognostic baseline variables. There's lots of related work on this dating back to at least 2001. It goes back even earlier in the survey sampling literature. But Yang and Ciatis in 2001, I'll talk about some of their work. But there are many people who have worked on this. And some of the material I'll talk about is from a paper in 2020 where David Ben-Kieser, Ivan Diaz, Alex Litka, Jody Siegel, and Daniel Sharfstein and I, we wrote a paper about using covariate adjustment for COVID trials. So that was near the beginning of the COVID-19 pandemic, and FDA had reached out to different statisticians and asked for recommendations on treatment trials that were starting up for COVID. And we recommended essentially use covariate adjustment because you don't have to be a specialist in COVID-19, even at that point in time, to know that there are certain variables that are prognostic for poorer outcomes if one gets a COVID infection. For example, age, older age, there are certain comorbidities. So yeah, I'll talk about that in a bit. I'll skip over this one. And I'll just talk about the simplest example. Actually, let me give a concrete example before I go into how to do covariate adjustment. So I'll do this demonstration using data from a completed trial, the TADS clinical trial. It was a treatment for adolescents with depression study. And the primary outcome, I'll just use 3 letters to keep track of here. Y is the outcome, the primary outcome. And here it's the change in the Children's Depression Rating Scale, revised CDR-SR score over 12 weeks. So the difference between the score at 12 weeks minus at baseline. This trial is more complicated than I'm letting on here. There were more than 2 arms, but I'm going to focus here just for illustration on the 2 arms. And so the A is the treatment assignment. A is 1 means assigned to treatment, that is fluoxetine. And A is 0 is assignment to the placebo control. And there were roughly similar numbers assigned to each, about 100, 110. And baseline variables. So here we looked at baseline, the baseline version of the primary outcome. Primary outcome is a change score, but the baseline CDR-SR score, that's one of the baseline variables. And then we looked at 8 others, and I'll show on the next slide. And the definition of baseline variable is anything measured on a participant before randomization has happened. And the idea is that baseline variables can't be impacted by the intervention because they were measured before randomization to the intervention or not. So part of covariate adjustment, it often involves fitting a regression model. And when you have a continuous valued outcome, the simplest method for covariate adjustment, which is a good method, is called ANCOVA. So it stands for analysis of covariance. And it's relatively straightforward. You pre-specify what the variables are that you'll adjust for. And I should say this is all in the context of a 1-to-1 randomized trial, the same probability of being assigned a treatment or control. There's some differences when you start to have either more study arms or you're trying to have a higher proportion go to treatment versus control or something like that. So that I'm putting that aside. So here we fit a regression model, regress the outcome, which is the change score in CDR-SR, comparing 12 weeks versus baseline. Regress that on intercept, beta naught. You put in the study arm assignment A, 1 or 0 as a main term, and then you can include baseline variables. So we have 9 of them. And I won't go through what each one is, but they're listed below, but they were all chosen because it's thought that they may be correlated with the outcome. They might explain some variation in the outcome that's unrelated to the treatment because these are baseline variables measured before treatment. And so you fit that regression model, and then in this one case, and then you use that regression model to generate an estimate of the treatment effect. In this one case, it turns out that the estimate is just the estimated coefficient on the treatment term. It's beta A, the estimated coefficient on the arm assignment term. And so that here it's minus 4.4. And so the covariate adjusted, the ANCOVA estimator is of the average treatment effect is minus 4.4, that many points in the change score. But I was hesitant to even put the slide, but it's because in general, you can't just grab a coefficient out of a regression model and say, this is my adjusted estimator for the average treatment effect. It does work for ANCOVA, but I'll talk about a little later. There's a more general procedure using, if you're familiar with the margins command, I think that's in Stata, that's a general procedure to get out average treatment effect using regression model fits. But the bottom line here is that the estimate of average treatment effect here from ANCOVA is minus 4.4. And so here I have a table which is summarized. So the primary analysis in this trial was not the adjusted estimator, it was the unadjusted estimator, which is somewhat common to do. It would just look at the difference in the same outcome, but take the average outcome among everyone assigned to treatment minus the same outcome, minus the average of that same outcome for everyone in the control arm, just the difference in means. That's the unadjusted estimator. And so there was minus 1.4 was the estimated treatment effect, and a 95% confidence interval from -6 up to 3.1. The ANCOVA, the adjusted estimator, that's in the third column here, as I mentioned, it's minus 4.4 points, and the confidence intervals minus 8.1 to minus 0.7. And the main thing I want to focus on here is how wide the confidence intervals are. And the second confidence interval, the one for ANCOVA, is substantially shorter than the first one. The first one's width is about 9 points. The second one, the width is about 7 points. Notice they're both negative valued, the endpoints of the ANCOVA confidence interval. And so that shows the value added from adjustment, that you're reducing the variance of your estimator. You're squeezing out some noise. And you can estimate that variance reduction in the final column. It's 32%, and it's an estimate, but that's equivalent to if you shrink the variance of your estimator by 32%, which was the estimated here, that's equivalent to needing 32% less sample size to get the same information, to get the same power. And also it happened to be in this case that if you look at this fourth column, the impact of adjustment. So that's the difference between the ANCOVA estimator and the unadjusted. It was minus 2.9. So that's a pretty big difference. And it happened in this case to be enough to go from non-statistically significant result for the unadjusted estimator. The confidence interval includes 0 for that one. So versus the ANCOVA estimator, the confidence interval excludes 0. So you would be rejecting the null hypothesis of no treatment effect had that been used. Often that's not often happening, that it will change things that dramatically. But in general, the ANCOVA estimator is giving you a better estimator. And that sometimes will help, that if there really is a treatment effect, that will tend to show that demonstrate that there is one more often. And if there's no effect, it will tend to demonstrate that more often. It's not biased in any particular direction. It's biased, or it is just pushing you a little bit more towards what the actual treatment effect is, whatever it happens to be. But in this case, it actually did change. It would have changed the result, but it has to be pre-specified. You can't look at 2 of them and pick your favorite one. It has to be pre-planned in the analysis before the trial starts, what analysis you're going to use, including which baseline variables you'll use. I won't go through some details on this, but I'll just mention another study context that I worked on. And so and I'm going to skip through the details of what the outcome is and the study arms and the baseline variables, and just cut this. But the context is Alzheimer's disease trial, and it was a trial. This is in planning a future trial for a treatment this is population of individuals with mild cognitive impairment. And we looked at a past clinical trial that was completed to try to figure out, well, would there be value added from covariate adjustment? Are there variables that are sufficiently prognostic correlated with the outcome? The outcome here is the clinical change in clinical dementia rating sum of boxes score at 1.5 years versus baseline. And there's a list of variables here that we considered, and looking at this completed study from the past by Peterson et al. In the same population and same outcome, adjusting for baseline variables led to a reduction of 23% in terms of the required sample size to achieve a desired power. So these trials cost tens of millions, higher even. And if you can reduce the sample size by 23%, or even in that ballpark, that's quite a lot of cost savings. It's also more ethical in the sense that you don't want to expose the least number of participants to your experimental treatment, the least number needed to determine whether the treatment works or not. Because it's unknown at the get-go whether it helps or hurts, so you don't know. So, so you can reduce the number of participants needed. You get the answer more quickly potentially because the trial duration is potentially less if you have a smaller sample size. Let's see, I'll just say for this slide, I'm going to skip a few things but the one feature of this method is that it does not involve making any model assumptions. No assumptions beyond what you assume for the unadjusted estimator to be consistent, to give you an estimator of the average treatment effect that at large enough sample size, as sample size grows, is converting to the true average treatment effect. And that's critical. We don't want to go making assumptions and building our analysis, a new analysis, for example, on new assumptions that if those assumptions are incorrect, then the new analysis is invalid. Here we don't make any additional assumptions. We're not assuming that model is correctly specified. And which is something the FDA mentions, that it's the ideal, and you can do this happens in covariate adjustment, is you can use regression models to construct your estimate of the average treatment effect, but in a way that is completely robust to the model being correct or not, which is sometimes hard to wrap one's head around. It took me a while to digest that when I started looking at this stuff. But the only assumptions, but I'll talk about it in a bit, but the only assumptions we're making are that the treatment is randomized. That means the treatment assignment is made independent of the baseline variables. And that we know to be true by design. Also, you can do something called stratified randomization, which is quite common and a good idea generally. All this works with that as well. And we also make an assumption that the participant data vectors, that each participant's data is independent of the other participants' data. And that's a common assumption made in analyzing clinical trials for the unadjusted estimator as well. Let's see. So we specifically do not make any assumptions about the relationships among the baseline variables, the study arm assignment, and the outcome, other than that treatment is randomized. And the reason we don't want to make additional assumptions and build our analysis on the foundation that these assumptions have to be right for it to be valid, because often a linear regression model or any kind of regression model, it can be certainly may be misspecified and is hard to detect. That can be hard to determine even from data, though sometimes it will jump out. So I'll skip over this part because it's but come back to it if there are questions about it. What it means to be misspecified, for example, for a linear regression model. So this would be the simplest model. This is the model that was fit. The third line here, the mean of the outcome y given study arm assignment and baseline variables b is beta naught an intercept plus beta 1 times a, the study arm assignment, plus beta 2 times b, baseline variable b. And that could be a vector. It could be not just one variable. You could have multiple the variables. And so the idea of a model being misspecified is that the true relationships among these variables, they could be, and I would guess they probably are, pretty complex. They're not. I think it's unlikely that things would have this simple linear form in practice. But we require our estimator to be consistent. That means converge to the average treatment effect, regardless of whether the relationships among these variables satisfy the assumptions baked into this model or not. So it's a good property. It means that the covariate adjusted estimator is completely robust. You're not making any model assumptions that when you're doing this analysis. And so in particular, when you write down a linear regression model, if you're typically doing it and assuming the model to be correct, that would entail that all the relationships between the average outcome and the baseline variables and study arm assignment, it's all linear. It's all lines. As you change the baseline variable, one of them or multiple of them, the impact on the outcome, average outcome, is moving linearly. And the other thing is that you're baked into this model is assuming that the treatment effect is identical for regardless of the stratum of baseline variables that you have. So it's saying that even for the people with the lowest disease severity coming into this, and the people with the highest disease severity coming into this, and the same thing with the age, and no matter which strata you look at in terms of baseline variables, that this, if you were to assume this model is correct, you're assuming the treatment effect is the same for everyone. It's going to move you, it's moving everyone up, or possibly down, or not doing anything from where they would have been if they didn't get the treatment by the same amount. That's true, at least within each stratum. All the people in that stratum on average are getting moved that much. And so we don't want to make an assumption like that. And we don't. Let's see. I'll just mention another scenario. This is some work that Josh Betts and I and others did a while back. This is involving the MISTY phase 3 stroke trial. We were planning that trial. This is in collaboration with the PI Daniel Hanley at Hopkins. And here it's a 0-1 outcome. The primary outcome is a modified Rankin scale being 3 or less at 180 days from enrollment. And this is the context is this is a new surgical treatment for one of the most severe types of stroke, intracerebral hemorrhage. And here there's the study arms, the 2 arms, new surgical intervention, MISTY intervention versus standard of care, that's the control arm. And baseline variables include NIH stroke scale, a measure of stroke severity, the clot volume, and the location. And we're still estimating average treatment effect, but here it's a 0-1 outcome. Modified Rankin scale 3 or less at 180 days, which is that's the dividing line between being able to walk unassisted or not on that disability scale. And we did simulations based on earlier data, the phase 2 trial data, and estimated about a 28% reduction in the required sample size if you adjusted for these baseline variables. There may have been slight differences, additional variables, or I can't quite remember, but exactly what we specified in the analysis plan, but it is similar, and certainly included NIH stroke scale because that's highly prognostic. And so that was built into the statistical analysis plan. The MISTY phase 3 trial was conducted. It had on the order, if I'm not mistaken, of 500 participants roughly. And at the end of the trial, the primary analysis, you adjusted for these baseline variables. And we did see, there you can look at the confidence interval we got that resulted from covariate adjustment and compare it to what we would have got if we did not adjust. And it was roughly equivalent to about 25% reduction in the required sample size. So it roughly lined up. That's not guaranteed, but at least in this case. And I'll say that stratified randomization, which I mentioned a little bit earlier, you might have a particular variable that you want to be balanced between the treatment and control arms, balanced by design. Say it's a high versus low severity and you want to make sure that the number of participants with high disease severity assigned to treatment is very close to that number assigned to control. So you can force balance by design. That's called stratified randomization. You stratify block randomization, for example, and that's generally a good idea. And the limitation is that you can't do that for a long list of variables. Maybe have a small number of variables, and they have to be either just 2 categories or maybe a small number of categories. And so the general advice, a rule of thumb, is stratify on what you can. So try to balance by design the variables that you can. So that will remove potentially some noise from your or the chance imbalances, that will remove some of them, and then do covariate adjustment on top of that for additional variables or more fine-grained versions of the variables that you stratified on. And they work best together. We have a paper that of my former PhD student, Binkai Wang, who's now assistant professor at University of Michigan, and some collaborators, Ryoko Susukida, Ramin Mushtabai, and Dr. Musume. We wrote this paper and talking about how to do that. And so then last we have some general recommendations on how to do this. We'll open up to questions right after this. But the one thing is, at the very beginning, you have to select your estimand, and often the simplest one would be difference in means. That's commonly used, or it could be a risk difference. You could also use a risk ratio or a relative risk. You can pick whatever estimand is appropriate, is most clinically important. And then for each estimand, there's a covariate adjusted estimator version for that. And the point here, this came up during COVID, in the earlier COVID days, when there were different scales for measuring outcome severity. There's a WHO scale for measuring different things, different levels that try to capture how bad your outcome is. And so it's ordinal valued outcomes. And one of the questions FDA was asking, and many people are asking, is, well, how do we, in clinical trials that were designed to test treatments for COVID, what should your estimand be? What summary of that ordinal outcome distribution should you be comparing in treatment versus control? So you could do difference of means, but there's an issue with interpretation, because going from level 0 to 1 or 1 to 2 could mean something quite different from level 6 to 7 or 7 to 8. There's something called a Mann-Whitney estimand, which is looking at the probability, if you pick two random individuals, assign one to treatment and the other to control, the probability that the one assigned to treatment would have a better outcome, with ties broken by a coin flip. And then there's some estimands based on log odds ratios. And our recommendation, this is from the Benckiser et al. Paper, was try to avoid, I mean, I'll say personally, I'd recommend this as a principle in life, generally, to try to avoid log odds ratios whenever possible, both because they can be challenging. I wouldn't say always do that, but in general, that would be my first, if possible. You might at least consider different types of estimands, that ones that don't involve odds ratios, because of interpretation challenges, number one, and computational challenges. They can be unstable sometimes. So the second point here is that like I've talked about throughout, the adjusting for prognostic baseline variables can potentially improve precision and power, and you have to pre-specify everything and exactly how you're going to do the whole procedure. So you have to tell if you're going to use a regression model, what will the variables be? You have to say how you're going to compute confidence intervals as well. So here, the simplest approach, or I'd say a good general approach, is something called a non-parametric bootstrap. But there are formulas that can be used as well. That's also possible. But it has to be all pre-specified. There should not be any room for making decisions later on. You also have to specify how you'll deal with missing data. So that's at the bottom of this next slide. I'll just start at the bottom of the slide and go up. So that you may have missing covariate values, and you also may have even more of an issue, maybe missing outcome values. People drop out, or and so we recommend using double robust estimator methods and potentially sensitivity analyses of robustness to assumptions. With missing outcomes, you always have to make some assumptions. And so we recommend these methods. And what's not something nice is covariate adjustment lines up. You can adjust for baseline covariates at the same time that you're adjusting for missing outcomes and as well. So the statistical methods for the missing outcomes, dealing with that, some of them are naturally line up with and combine with covariate adjustment. Let me just see that. I'm going to skip over some things, but we can come back if there are questions. But I want to leave time for that. But here are the bottom line pros and cons about covariate adjustment in randomized trials. I already mentioned the pros that you can, there's potential to improve precision, get tighter confidence intervals, require lower sample size to get the same power, and without making any additional assumptions compared to the unadjusted estimator that ignores baseline variables, say the difference of means. Let's see. One of my favorite points is the third one, this third pro, which is this is sometimes misunderstood, and I can see why. It's a little counterintuitive. So the third point is that covariate adjustment is useful in smaller trials, but I mean you have to have some minimum sample size. So I'd say that it's if it can't be used in very small trials, but it's valuable in smaller trials, but it's also above some minimum sample size, but it's also very useful. And in some sense, it's more useful in larger trials. So it's useful across the board generally, but larger trials you get on an absolute scale, you can get a larger benefit because the sample size reduction is a % reduction, and it's not the same, but it's similar at different sample sizes. So if you have a 10% sample size reduction in a 100 participant trial, that gets you from 100 down to 90. I mean, that's good. But if you have a 1,000 participant trial, going from 1,000 down to 10% less down to 900, I mean, that's 100 participants less. That's on absolute scale, that's a bigger, that's larger improvement. And I've heard multiple independent sources saying that this false intuition that, well, in a large enough trial, things will be balanced out between the study arms. The baseline variables will just be balanced out anyway because of randomization in larger trials. So we don't have to worry about adjusting to try to fix it up. It fixes itself. That it is true that you get better balance on average in larger trials, but it's that the conclusion that we don't need to do, or it's not worth it, there's no value added or less value added from covariate adjustment, that's not correct. In fact, that's one of the places where I would say the pros so much outweigh the cons, typically in larger trials. But there is a con I haven't mentioned, which is an important thing to keep in mind, is that if you adjust, the worst thing that could happen would you be adjusting for baseline variables that you thought they were going to be correlated with the outcome and explain some of the variation in the outcome, but they weren't. Maybe in the previous data set that you looked at, they were correlated, and there's a biological reason to think they would be correlated, but in your actual trial, they weren't, because of potentially some differences between your trial and what you looked at in the past. And if you adjust for sort of a useless variable, a variable that's unrelated to the outcome, a baseline variable, then that doesn't affect consistency. You still, but you can you won't gain any precision from that, and you could lose some precision. And the rule of thumb, roughly speaking, is that for each degree of freedom that you put into your regression model that is wasted, that is that you might have a variable that measures something that ends up being unrelated to the outcome, or at least or you've already covered it by having other variables in there, that it doesn't add anything new in terms of reducing the variance in the outcome by adjusting for it. For each degree of freedom you add, it's equivalent to having one less in your sample size. Each degree of freedom that's completely wasted. So there is a cost, and that cost hurts you more in the smaller studies in a sense, because if going from 100 participants down to 99, that that hurts more than going from 1,000 down to 999 participants in terms of power and precision. So you do need to have prognostic baseline variables. You can't just throw in a bunch of variables you think might help and then hope for the best. I would not recommend that. But you want to look at past data sets with the same population and outcome, and see which variables are correlated and how much of the variation in the outcome do they explain. And as one way to figure out which variables to consider for covariate adjustment. And then you can look at what people have done in the past also. In the stroke trial literature, there are a list of variables, especially in ischemic stroke, that are consistently helpful and reduce the required sample size by an equivalent of about 25% across a bunch of different studies, 6 or 7 studies. And so that gives me confidence in a future trial in a similar population, similar outcome, similar disease area, that you'll probably get a pretty good around that amount of benefit in your future trial. But I will say stroke trials are, that 25% improvement is generally around the best case that I've seen. Sometimes you don't expect always to get that. You might more typically get something, this is just roughly speaking, in the range 5 to 20%. Sometimes you'll just get 1% or 2%, or in the worst case, nothing. You could, but don't just put a variable. The more variables you put in at a fixed sample size, that you potentially are hurting yourself by if they're not adding any prognostic value. And there are resources, and I think Josh has put in a bunch of thank you, Josh, for responses in the chat. There are resources. We have our FDA short course video recording that's you can watch if you're interested in learning more about this, where we presented some of our work to the at FDA. And I'll just stop there. And there's a long list of citations on this, and grant support for this as well. And I do have to mention one last thing, that when you're estimating the standard error, you're constructing confidence intervals or doing hypothesis tests, computing a p-value, you have to take into account that you use covariate adjustment for it. The methods for getting standard error or a confidence interval or a p-value or hypothesis testing, the methods that you use along with an unadjusted estimator won't necessarily work if you use some of the covariate adjusted estimator. You just have to use a method that lines up with that estimator. So that's one thing to keep in mind. It often involves using something called a robust variance estimator. But I want to mention that before I forget. And thank you all so much. And let me for listening, and I'll open it up to questions.
Awesome. Thanks so much. I am actually just going to hand things over to Josh Betts, who is going to handle the Q&A, but thank you for that great overview.
So currently we only have one question in the chat. So if you do have any questions, now is the time to add those into the chat. We have one question about clarifying the difference between the average treatment effect, the ATE, and the average marginal effect, the AME. So people may be familiar with average marginal effects from the margins command in Stata, the margins package, or marginal effects in R. Could you clarify what the difference is between the average treatment effect and the average marginal effect?
Yeah, I'm not familiar with the term average marginal effect, but I think it's the same thing. It's sometimes called the marginal treatment effect, which is marginal and average mean the same thing generally, in all the contexts I've seen. And average is probably a better word than marginal. It's just a little more understandable. So so here we're looking at the average treatment effect. And also, I should have mentioned, so that was in the title of this talk, is that this is covariate adjustment for estimating the average treatment effect. And that's often of interest. One of the key things of interest in the clinical trial, in a randomized trial, was the average effect. And you can also use covariate adjustment. This is where things start to get confusing, but you can also use covariate adjustment to estimate conditional effects if you're willing to make model assumptions. Now, my preference is not to make those assumptions. So that's one thing that makes me, I like estimating marginal treatment effects, but it's also possible to estimate conditional treatment effects. That's treatment effects within strata of baseline variables. That's something also that's important. I want to know about that. It's important to know about that, but it often requires making assumptions that may or may not be correct. So, yeah, so that's but anyway, marginal or average, they generally mean the same thing.
I have a question about the interpretation of coefficients in the regression model if we're doing covariate adjustment. So you talked about in your example with the TAD study that here we're using a linear model, and here the ANCOVA estimate happens to be the same, but in general, that's not true when you go to a nonlinear link. And the interpretation of your regression coefficients, we're not just using a regression model and taking a regression coefficient from those and calling that our covariate adjusted estimator. So can you clarify, how do we go from the simple example of ANCOVA and generalize this to kind of other types of outcomes, such as like a binary outcome or an ordinal outcome?
Yeah, that's a great question. And so here's the idea. And it is right that you don't, in general, in covariate adjustment for marginal treatment effects, you don't want to grab the coefficient on, say, the treatment term in your regression model and say, that's it. This is my adjusted estimator of the average treatment effect, because the reason is that, say you had a logistic, the simplest case to talk about is logistic regression model, where you have a binary outcome, just a 1-0 outcome. The example, to make it concrete, that I talked about is the MISTY trial, where you have being able to walk unassisted or not. It's a modified Rankin scale 3 or less at 180 days from enrollment. So there you could use a logistic regression model instead of a linear regression model. And so and actually there's a typo here in this slide that I'm showing now, that it shouldn't say mean, it shouldn't say E of Y equals 1, it should be the mean, the expected value of Y. The equals 1 shouldn't be there. But that actually is because I used a similar slide template to do the 0-1 case. And the only change is that you put an inverse logit on the right side. Inverse logit of beta naught plus beta 1A plus beta 2B. You fit a logistic regression model for the outcome Y given study arm assignment A and B. But instead of, if you were to grab the beta 1 hat there, if the model is correctly specified, then that has an interpretation as a conditional odds ratio or log odds ratio. I always would have to check that, but I generally recommend avoiding things like that. But and that's only if the issue there is that the interpretation of that is different depending on the variables that you adjust it for. So if you did that in one study and then you did another study with the same population, but say a different treatment, and you looked at the effect, or you just had a replication, you had two trials of, often there are two trials to demonstrate effectiveness of a new drug, for example, or a medical device. If you adjust for different variable sets, then the interpretation of the conditional effect changes unless you're in a special case of continuous outcome. But for binary outcome, logistic regression, the interpretation changes depending on the baseline variables you put in, and it's all dependent on the model being correctly specified, which is probably not the case. And when the model is misspecified, then there's no interpretation to give to that coefficient. So those are the issues with conditional effect. But what you can do is basically you do something, it's called standardization. That's one way to say it. So what I have here is kind of a long, it looks like I'm doing extra work, but it's to show you the more general procedure for computing the a covariate adjusted estimator that works with essentially any kind of generalized linear model with canonical link function, which is just some jargon, but it basically means like if you could do it for logistic regression or Poisson regression, the same thing. And so here's, in this case, it will just reduce down to grabbing coefficient. But if you had a logistic regression here, what you would do is, and you could do it with even without logistic regression, just with this, you do the model fit, and then for each participant, just using their baseline variable B, or vector of baseline variables B, but I'll just say, let's just say, pretend it's one baseline variable for simplicity. You fit the model once on all the data, then and then for each participant in all of the data, you just plug in their baseline variable and plug in A as 1. You essentially, you set in the model A as 1, and then you generate a predicted value. So for a binary outcome, it would be predicted probability of Y is 1. Had essentially setting A is 1 in the model, so you plug it, there's beta naught hat, your estimated beta naught, setting A is 1, that would be the second bullet here, that that would mean you have a beta 1 hat showing up, and then you put in BI, the ith person's baseline variable, times beta 2 hat. So that's setting A is 1 of the model fit and getting a prediction for everyone in the data set, both arms. This is where actually the value, that's how covariate adjustment, you get more information. And then take the average of those predictions, predicted probabilities, or and then if it were 0 on outcome, the same thing, you do it for setting A is 0. Set A is 0 in the model fit, that makes the beta 1 hat disappear, and then generate a predicted mean outcome or predicted probability of 1, setting everyone using just people's baseline variables, and then take the average of those. And then what that gets you is an estimate of the average outcome if everyone had been set to control A is 0, and an average, that's mu0 hat. Mu1 hat is an estimate of the average outcome if everyone had been set to treatment. And then you can contrast those. So you can take the difference if you want the mean difference, or for a binary outcome, the risk difference. If it were a binary outcome, you could do a ratio, could be the risk ratio. And sorry if it's a bit confusing, I'll try to, in my mind, change this to be logistic regression versus not. But this procedure, it does reduce, in this case, a linear regression to just grabbing that beta 1 hat coefficient. But the general procedure of doing this, because terms would all cancel except for beta 1 hat when you subtract mu1 hat, when you subtract mu naught hat from mu1 hat. But if it's logistic regression, things are not going to cancel because there will be inverse logit involved. And but that does give you that will give you an estimator of the average treatment effect on the correct scale. And that has these nice properties so Ciatis, I didn't mention this amazing result of Yang and Ciatis from 2001. They showed that this is for the continuous outcome case, that the estimator, this covariate adjusted estimator in COVA, is consistent, which is true also for the logistic regression with the variation I said. It converges to the average treatment effect. And it does not require any assumptions about the model being correctly specified. They also showed that in a 50-50 randomized trial, equal randomization ratio to the treatment versus control, that it will either at large sample size, so asymptotically, you get the same or better precision as the unadjusted estimator. So it can only help you or not change anything as long, in this, but that's at arbitrarily large sample size. At finite sample size in real world, you have to be careful about the trade-off of how many variables we put in versus your sample size. Because of this issue I mentioned at the end of it, if you put in a variable or use up a degree of freedom and it's wasted, really your variable it's like putting in noise to something unrelated to the outcome, then it's like losing one participant as a rule of thumb. And so, yeah.
Thanks very much for that. And then for those that want to see this actually in practice with software of how do you do this marginal standardization or G computation, there's an example in the links provided earlier. There's a very important question and clarification here. Somebody's asking about if a variable lies on the pathway between the treatment and the outcome, how should that be handled? So that would be a post-randomization covariate.
Yeah, exactly. So that's a great question. And so all of this covariate adjustment, I wish it had been called baseline variable adjustment. Covariate refers to baseline variable, and baseline variable means measured before randomization has happened. So that's where all of this is about, adjusting for baseline variables, things measured before randomization. And so by design, they cannot be things that are impacted by the treatment, which gets, whether you even get treatment, which one you get, or if you get control or the treatment, that's not even determined until after the baseline variable is measured. So unless there's some time machine type scenario, then baseline variables are not on the pathway between treatment and the outcome, because they happened before the treatment got assigned. The treatment can't impact them. Now, so that the setup involved, that's critical for all of this. It's all about baseline variables. Unfortunately, they're just called covariates, but they should be baseline variables. That's what it means. And there are, I will say, to deal with missing outcomes as a separate thing, when you're trying to deal with missing outcomes and do adjustment, doing analyses that try to deal with potential bias caused by missing outcomes, if people are more likely to drop out if they have certain trajectories or are in certain strata, and there are methods to deal with that adjust for that, that do involve variables measured after randomization. And so there, it's justified to do it, but there you need assumptions. You need to make assumptions when dealing with missing outcomes. So there are methods, especially when you have longitudinal data, you're going to have all things measured after randomization. You can't treat it as if it's a baseline variable, but you can still adjust for it. There are techniques that combine covariate adjustment, which means the baseline variables, and also adjusting for things measured after randomization, but they require assumptions, like any method that deals with missing outcomes. Yeah, good questions. And actually, that's how this works, is because by design that these are variables not on the pathway. If they're on the pathway and can be impacted by treatment, you don't want to adjust for chance imbalances, because those imbalances on those post-randomization variables, it could be caused by the treatment. That you want that, or you want to measure that. You don't want to adjust it away or something, because then you're messing up that's the wrong thing. The reason it's okay and it's a good idea in a sense to try to get back to where you would have been if there had been perfect balance on the baseline variables, is that squeezes out some of the possible noise, when you look at the difference in the mean outcome under treatment and control, if just by chance a few more high disease severity participants had been assigned to treatment versus control, or the other way around, then that will tilt things one way or the other. Say it were the case that those with higher disease severity have worse outcomes on average, regardless of what treatment or control they get. Then if you have a few more of high disease severity participants in the treatment arm, this is all just intuitive, roughly speaking, then the treatment is going to look a little worse than control, everything else being equal, and vice versa. If they had been a few more high disease severity participants who are going to have worse outcomes on average in the control arm, that would make control look a little worse than it really should. It's going to kind of tilt things one way or the other. And the idea is, well, fix that. And it's something you can fix because you can measure it, and you can essentially say, well, why don't we instead of just comparing average everyone in each arm and compare those numbers, do it separately within strata. This is the intuition of it. Look at everyone who has high disease severity in treatment and control, compare their average outcomes to each other. Do the same thing for those with low disease severity in treatment and control, compare their outcomes to each other, and then estimate treatment effects essentially within the strata, and then combine them to get an average treatment effect. And when you combine them, you use what proportions you use is based on the pooling all the baseline variable data across arms. So that's how it works. It adjusts for those things. And to be honest, if I were, because I work on this all day, I'm sure I have bias from that of wanting to do this, but also just my intuition is that if I saw in a study report that treatment did better, people under treatment did better, but also by chance there were healthier people to begin with in treatment, or people who had less disease severity, I'd want to see the analysis where you equalize that and then see does that wash out the treatment effect? Then it was just a statistical artifact, versus if you adjust for that, okay, that changes it, but still not by enough to change the conclusions of the study. So I'd want to know, was it because of the imbalance of the baseline variables or not? So good.
One question we have is when today we're talking about covariate adjustment in individually randomized trials when treatment is assigned at the individual level. But is it possible to kind of generalize these things to studying interventions where it may be assigned at an organizational level that's more common in implementation research?
Yeah, great question. So that's ongoing research, but there are others there are papers and others who have applied covariate adjustment to cluster randomized trials where it's not just individuals get randomized, but the randomization unit is a cluster where an intervention clusters where intervention is assigned versus not assigned, or different interventions are compared to each other. And you can use covariate adjustment in those as well. And I'd say it's probably underutilized there also, because you could have variables at either the cluster level. Say it's a hospital. The cluster is a hospital. There might be features of the hospital that are correlated with having better or worse outcomes. And you'd want to adjust for those things if possible. And so they're cluster level. You can adjust for cluster level variables, also individual level variables. So if something for all the participants, essentially the population, the people in a particular hospital, the participants in the study, if they have higher disease severity, that you can adjust for that as well. So there you have kind of two sets of variables that you can use, and it's a more complicated, just like cluster randomized trial analyses in general are more complicated. But yeah, you can use it there too. And that's some work in progress that I'm working on through the ALACRITY Center, is to look at some implementation science trials and try to look at, well, what would be the value added in trials that were already conducted, to look back on data, and then try to write up papers on, well, what happened in those scenarios? Is it worthwhile to do or not? How do you select variables? Try to answer questions like that to help for those designing future studies to plan that in or not, if it doesn't make sense. Yeah. Great. Any other questions, or and you can always feel free to email me if you'd. There are a few topics that I could talk about forever and will continue to be excited about and passionate about, and this is one of them. There are a couple others. One is community solar, and there are a couple others. But yeah, I'm always happy to discuss this. And if you want any advice or help or just support on clinical trials that you're designing, please reach out. I'm happy to try to help if I can.
I will jump in. Thank you so much. I love the reference to community solar. So if anyone wants to reach out on anything, This was really a fantastic session, really great overview. And then the questions were just fantastic. Thanks, Josh, for moderating that, and Michael for answering them all. And thanks to all of you for staying engaged. And I especially love the questions that sort of people were clearly grappling with, like, okay, how do I actually use this in practice and in my world of, sort of mental health services research. So I think huge success already. So I hope this was helpful to all of you. Thank you for sticking in. I'm thrilled with the number of people that also are still on. So thank you all. We will, I guess, end the webinar, but again, feel free to reach out to any of us with any follow-up questions. And there are, of course, lots of links and resources shared in the chat that will be able to help as well. And you can watch the recording of this if you want to refresh after it's up on YouTube. So again, thank you all, and stay tuned for the next webinars. We have a few more scheduled for the rest of this academic year, so stay tuned for announcements on those. Thank you very much.
Thank you. And I just want to thank Josh, and also say that we'll share, if it's not already been done, share the link to the FDA short course we did on this. That also, it's a longer version, if you that gets into some more detail if you want to see this expanded. Great, thanks.